Let's build a custom gym-compatible reinforcement learning environment. This exercise is broken out into 3 modules. The problem module strictly models the rules of the problem, how one interacts with the problem, and how the interaction affects the problem. It doesn't necessarily have an understanding of reinforcement learning. This could be a business problem or the snake game that you just coded. The wrapper module makes the problem gym compatible, converting it into a reinforcement learning environment. In the solution module, we'll use 2 ways to train the agent, one using basic Q-learning and the other using the Stable Baselines3 reinforcement learning library. Okay, so here's the super simple scenario. We got a warehouse and we got a robot working in the warehouse. The warehouse is divided into a grid and the robot's gonna start at position row 0 and column 0. There's gonna be random targets generated throughout the grid. Let's say right here. Let's say there's an item on the shelf at that spot and the robot's gotta go there. When we perform the reinforcement learning, we want the robot to be able to find its way using the best path to any target on the grid. Again, this is super simple, doesn't need reinforcement learning at all. Maybe in the future, we can add obstacles and other random stuff that happens in the warehouse. This is what we got right now, so let's jump to the code. Okay, I'm in this version 0 warehouse robot Python file. As you can imagine, with this simple problem, you can accomplish this in basic Python pretty easily. So I'm not going to spend too much time on the code here. So I'm going to go over it pretty quickly. Over here, we define the actions that the robot can take, which is basically left, down, right, and up. Right here on grid tile, this is for printing out the layout of the warehouse, where the robot is and where the target is. I overrode the string function. This returns the first letter of these names. So when we do a print, if we try to print a floor, it's going to print an underscore, a R for the robot, a T for the target. So we're not rendering anything on the screen other than using basic print statements. In the warehouse robot class, we can define the size of the grid. We'll call the reset function, which always starts the robot at position 0, 0, row 0, column 0. We'll optionally pass in a seed so that we can do reproducible executions. This is where we randomly generate the target position. Next is the perform action function, which takes in a robot action. This basically just moves the robot around on the grid, making sure the robot stays on the grid, and will return true if the robot is at the target. In the render function, all we're doing is looping through the grid, row by column, and just printing out where the robot is, where the target is, and the floors. Okay, that's it. Down here, we got a couple of lines of code to test the code above. So let me run it just to show you what it looks like. Okay, it ran. Let me scroll back up. The robot starts on the top left. The target is at row 0, 1, 2 and column 1. We're randomly picking an action. Action is down. So we can see that the robot did go down. The next action is right. The robot did go right. Okay, robot goes left, goes back to here, it tries to go left again. We won't let it go off the grid. It looks like the code works just fine. Let's move on. I'm in the warehouse robot _env file. This is where we convert the problem into a gym-compatible environment. Up here, I've linked to a guide on how to create your custom environment. This is more involved. It's a little bit more complicated, but you can check it out if you want. I'm importing a couple of Gymnasium modules. I assume that you have Gymnasium installed. If not, check out my playlist. I have a guide on how to install it. I'm importing my warehouse robot module right here, also NumPy. Here I'm calling the register function to register this module as a gym environment. Once registered, the ID is usable in this gym.make function. The ID here, we can call it whatever we want. This is the usual convention. The entry point points to this module, which is the name of the Python file without the .py, colon, and the class name. The class name being this one. So this is our implementation of the gym environment. Our environment class needs to inherit the gym.env parent class. Here's a link to the API if you need it. Metadata is a required attribute. Within metadata, there is render mode and render FPS. In our environment, we have two choices, either none, it's implicitly defined, so we don't need to specify it here. If it's none, then we're not going to render anything onto the screen. If it's human, then we are going to render stuff to the screen. With the built-in gym environments, when you put human here, they usually use Pygame to render their environment, and FPS, frames per second, is used to control how fast they render the graphics. But for us, since we're just printing stuff to the screen, we're not really rendering anything, so this frames per second is just a dummy value here. In the init function, we'll take in the size of the grid and use that to initialize our warehouse robot. We'll also note down the render mode. Gym requires that we define the action space. The action space is the robot's set of possible actions. In our training code, we're going to call action space.sample to randomly select an action. So that's how the action space will be used. We use the gym spaces.Discrete class to define the action space. Let me jump back to the robot actions. So the robot actions are basically from 0 to 3. So when we pass in the length here, the length of 4, our discrete is going to go from 0, 1, 2, 3. So this just happens to match up with the robot actions. If the robot actions are not this straightforward, if it's like 1,000, 2,000, 3,000, 4,000, then we're going to have to divide by 1,000 to convert the actions to work with the discrete space. So let me jump to the discrete class. I'm holding down Control and then clicking on the class name. In the discrete class, it takes an n, the number of elements in this space. We passed in 4 here. We didn't pass in the start, so by default it starts at 0, and with a length of 4, it goes from 0 to 3. So keep this in mind that we need to map the problem's possible set of actions to this discrete space here. Gym also requires us to define the observation space. When an action is taken, what is the state of the problem? What is the impact of that action? That is the observation. For us, we want the robot to be able to navigate to a target regardless of where the target is. So for that, we need to observe the robot's position and the target's position. And we can do that using a one-dimensional vector that looks like this. The first 2 elements are the robot's position, and the second 2 elements are the target's position. We use gym's spaces.Box class to define the observation space. How this works is first we define the data type. Since we're in a grid, we're using integer, but usually boxes is used with floats. So if we use floats, we can put the robot and the target anywhere inside the box. But since we're keeping things simple, we're just using a nice and neat grid. Now for the 4-element array, we define the shape here. The high and the low is used to check the boundary of these values. Since all of their positions are going to have a minimum of 0, we set the low to 0. For max, what we do is, since it's a 4-element vector, we pass in a 4-element array here. This first element here is the maximum of the robot's row position. The second element checks the robot's column max position, and same thing for the target's row position and the target's column position. The observation space is used to validate the observations returned by the reset and step function that we'll take a look at down below. Gym requires us to implement the reset function. In our training code, usually at the beginning of each episode, we'll call the reset function to reset the state of the environment. Gym requires us to call the parent class's reset function and pass in a seed. This is used to control randomness if you want to be able to reproduce the scenarios. We'll call the warehouse robot's reset function. Let me go there. All it does is initialize the robot's position and generate a random target position. We'll use NumPy's concatenate function on the robot's position list and the target's position list. And all it does is convert the format that we defined up at our observation space. We can also return some debugging information just included in this dictionary here. If render mode was set to human, we'll call the render function. Let me scroll down. In the render function, all we're doing is calling the robot's render function. Okay, now we return the observation along with the info. Gym requires us to implement the step function. The step function takes in an action and applies it to the environment. Here all we're doing is forwarding the action into the warehouse robot's perform action function. Let me go there. Okay, we move the robot to the next cell and then return true if the robot reaches the target. We'll keep track of that right here. The step function needs to return a couple of things. First, the observation, which is after taking that action, what's the state of the environment? So here we construct the observation just like the reset function. After taking that action, where's the robot? Where's the target? We need to return the reward. The reward influences how the agent is going to learn, how the robot is going to learn. So in this case, when the robot's moving around on the grid, we're not giving it any reward. But if it reaches the target, we'll give it a reward of 1. We'll also signal that the scenario is done. So we'll set terminated equal to true. So those two things gets returned here. Reward is something that you need to play around with to see how it influences learning. The next thing that needs to be returned is truncated. This is if you want to set a limit on how many actions, how many steps the robot can take. Let's say after 200 steps, you want to stop this episode. This is how you can do it using the truncate parameter. For us, we'll just let the robot wander as long as it takes to find the target. So we'll just not use this parameter. And info you saw from before, this is where you can set debugging info. Gym also requires us to define the render function. Here all we're doing is calling the robot's render function, which just prints the grid and where the robot and target is. The main function is where we can check that our environment was created correctly. Remember up at the register function, we registered this ID. So that makes it possible for us to use it in the gym.make function. By calling gym.make, we're creating an instance of the environment. We'll call the check environment function. This is a gym provided function that checks the environment to make sure it's correct. Now gym automatically wraps the environment in a bunch of different wrappers. By calling unwrap, we can make sure that check env is checking our module, this module here. So assuming the check environment is correct, we'll test the environment ourselves by calling reset. We'll grab the observation from the first index and we'll just do 10 actions. Here we use the action space called sample to select a random action and pass that random action into the step function. And then we'll just do that 10 times. So let me run that. Okay, let me scroll up. If you run this a couple of times, you might see this warning here that we already registered our environment and it's overriding it again. So it's okay, just leave that. When we call the check environment function, it automatically calls reset and step, runs through a bunch of checks, and we don't see any errors. So it looks like we're good. Now inside our own check, our own loop here, our robot is on the top left, the target is on the bottom right, and we're just doing a bunch of random actions to make sure that nothing is broken. We're not trying to learn or solve this environment right now. We're just taking a bunch of random actions, making sure that, let's say it goes down, it actually goes down, so it looks fine. Now let's try to break the environment and see what the check env function reports. Let's say I don't create a step function. Let me just throw something here. Run this code and see what check env reports. It's not very specific. It's throwing a not implemented error, which is correct. We did not implement the step function. I wish the description is better, but Let me put this back. Now let's see. Render frames per second. Let me put a 0 here. Run it again. So this is a much better message. It's expecting render FPS to be greater than 0, and the value that I set it to is 0. The check-env function does work. Let's move on. Let me make sure I change this back. Okay. Now that we have our custom gym environment, let's try to train it. I'm in the warehouse robot train module. As mentioned before, I'm going to use two methods to train the environment. First one using Q-learning and the second one using the Stable Baseline3 library. First, Q-learning. Now, I already did several videos on Q-learning. If you're interested, check my playlist. You get more detail on the Q-learning code. So I'm going to go through this quickly. We'll create the environment here. Our Q table, it's going to be a 5-dimensional vector. These are the 5 dimensions. First 2 is where the robot is. The next 2 is where the target is, and then the last dimension is the actions. If we're training, we'll create the Q table. If we already did the training and we're doing a test, then we'll load the Q table from a file. We'll set the hyperparameters here. I'm using an array to keep track of the number of steps that the robot takes per episode before it finds the target. At the beginning, the robot is going to wander around many steps before it finds the target. Near the end of the training, we expect the number of steps to be pretty much minimized. We'll keep track of the steps and then we'll graph it as well. I'm going to loop through the number of episodes. This is a parameter that we pass in. We set the environment. And we're using epsilon greedy here, so either we're selecting a random action or we're looking up the Q table to find the best action at the moment. We'll execute the action and update the Q table, okay? So this keeps going until the terminated flag is true, which means the robot has found the target. And then we decrease epsilon, and then we'll go to the next episode and repeat again. That's Q-learning. Let me go down to my main function here. First, I'm going to train for 1,000 episodes. After that, we'll run a test. Okay, hitting F5. This should be done pretty quickly. Okay, the training is done. Before I review the steps, let me go to the graph of the training. This is a graph of the episodes down here on the x-axis and the number of steps taken on the y-axis. As expected, at the beginning of training, the robot fluctuates around 50 to 60 steps before it can find a target. Over time, as training progresses, the number of steps to reach the target decreases. Near the end, it pretty much falls below 10 steps. The pickle file, this is a binary file. We save the Q table here. Since it's a binary file, we can't really look at it. Okay, after the training, we ran one test with rendering on. Let me scroll back up. Okay, so this is the test. We'll start here. The random target is here. The best action is to go down and then go right again, go down. Okay, so our Q-learning works. The next thing that we're going to do is to train with the Stable Baseline library. Let me comment out the Q-learning. Let me do the training first. I've also done a Stable Baseline3 video. Make sure you check that one out. I'm going to go through this quickly. As you can see, it's no more than 10 lines of code. We'll create an instance of the environment. We'll use the A2C algorithm to train the environment. This is just something I randomly picked. Down here, we're doing an infinite loop. We're basically performing training indefinitely, and then every 1,000 time steps will save the model. Let me start the training, and then I'll show you when I would stop the training. Hitting F5 here. You'll see in a second on the left, you're gonna see a models folder and a log folder. Okay, after 1,000 steps, you can see that the model is being saved here, and also the library is logging events here. Now, as training is happening, I'm going to create a new terminal. I'm going to bring up TensorBoard. I'm going to pass it the logs folder. TensorBoard is started. I will go to this URL TensorBoard is looking at the logs folder. It's graphing some information that we can use to determine if it's time to stop the training. On the top left, this graph is graphing the episode length. That means how many steps is the robot taking before the episode ends. And this looks pretty close to the Q-learning graph. You can see that the model is already solving the environment. So any more training, we're not going to get any more efficiency. So at this point, we can stop the training. We stop the training just by stopping it right here. So we got way more than necessary. I think the 1000 step model is already good enough. So let's test it. Comment out the train function and comment the test function. The test function, all it does is load. We're loading the 2000 time step, which is this one right here. Predict is going to get the best action based on the environment. After picking the action, it's just gonna execute it. Let's run this. Okay, let's check. We start up here, targets here. First action is go down, go right, go right, go down, go right, and go right. Looks like the training works. All right, we made a custom environment and we trained it. If this was helpful to you, be sure to give me a like and subscribe and leave me a comment on what environment you're planning on making.